We will talk about joint distributions today. So the basic goal is that we want to study more than one random variable simultaneously. We will only work with pairs of discrete random variables. The case when we are working with continuous random variables is almost exactly the same. The only thing that will change is all the sums would be replaced by integrals. So let x and y be two discrete random variables. Then the joint probability mass function, that is the joint PMF, is given by the probability function px comma y, which is basically the probability that the random variable capital X takes the value small x and the random variable capital Y takes the value small y. Now suppose x takes values inside the set script x and y takes values inside the set script y, then we can think of the joint PMF px comma y as a function from the Cartesian product x cross y to the set of real numbers R, where the pair x comma y goes to px comma y. The values of px comma y have to satisfy these two conditions. The first condition being that for all values x comma y, px comma y will lie between 0 and 1. And the sum of all px comma y for all pairs x comma y must add up to 1. There are two important distributions associated with the joint probability distribution, which are the marginal and the conditional distributions. We begin with the marginal distribution. Fix x inside script x. Then the marginal density with respect to capital X is the sum over all y inside script y of the probabilities px comma y. This is sometimes called as the marginal with respect to x. For a fixed y, the marginal with respect to y is defined in an analogous manner. And finally, for a pair x comma y inside script x cross script y, the conditional distribution or the conditional probability of y given x is given by the quotient px comma y divided by the marginal px of x. And the conditional probability of x given y is given by the quotient px comma y divided by the marginal py of y. These are exactly the conditional distribution of y given x and the conditional distribution of x given y. We are now led to a very important formula which relates the joint probability distributions with the conditional distribution and the marginal distributions. This formula plays a very important role in probability. The first application is going to be the definition of what it means to say two random variables are independent. We say that the random variables x and y are independent if the probability of y given x equals the marginal distribution of the random variable y for all choices of x comma y inside the Cartesian product x cross y. And this latter condition will be true if the joint probability distribution px comma y equals the product of the corresponding marginal distributions with respect to x and with respect to y for all choices of x comma y inside script x cross script y. We next talk about expected values and variations for combinations of random variables. Suppose h is a function that is defined on a pair of random variables x cross y. Then the expected value of hx comma y is defined as the following sum, where we're summing over all pairs inside x cross y of the product hx comma y times px comma y. We use the definition of expected values to define the covariance of x and y as the expected value of the function x minus mu x times y minus mu y, where mu x is the expected value of x and mu y is the expected value of y. The product x minus mu x and y minus mu y is going to be positive if both x minus mu x and y minus mu y are positive, right? So which means that uh, for large values of x, we will have large values of y, which would imply a positive relationship between the random variable x and y. Similarly, for large values of x, we have small values of y. The product x minus mu x times y minus mu y ends up being negative, in which case the covariance is negative. So ends up giving a negative relationship between x and y. There is a nice shortcut formula to calculate the covariance, which is going to be the expected value of x times y minus the expected value of x times the expected value of y. To summarize, the covariance is the expected product of the deviation of x from its expected value mu x and y from its expected value mu y. So depending on whether the covariance is positive or negative, we would have a positive relationship between x and y or a negative relationship between x and y. However, there is a small problem, which is that the covariance depends on the units in which x and y are measured. To take care of this problem, we define the correlation coefficient of x and y, which is calculated as rho x comma y given by covariance of x comma y divided by the standard deviation of x times the standard deviation of y. One can see that the correlation coefficient does not depend on the units in which x and y are measured. Let's understand some properties of the correlation coefficient rho x comma y. Suppose A and C have the same sign, then the correlation coefficient of the linear combination ax plus b, comma cy plus d is going to be the same as the correlation coefficient of x comma y. The correlation coefficient of x comma y will always be a constant number that lies between -1 and 1. Furthermore, the correlation coefficient will take values plus minus 1 if and only if there exists a constant a not equal to 0 and a constant b such that y is equal to ax plus b. That is, x and y have a perfectly linear relationship. In general, the correlation coefficient measures the extent of linear relationship between x and y. Finally, it is important to note that if x and y are independent random variables, the correlation coefficient is going to be 0. Note, however, that the correlation coefficient equal to 0 does not imply that x and y are independent. In this scenario, all we can say is that x and y are uncorrelated. That is, there is no linear relationship between the two of them. We finish up this video by talking about linear combinations of random variables. Okay, suppose we have n random variables, x1, x2, x3, all the way up to xn, and a1, a2, all the way up to an are n numeric constants. Suppose the expected value of xi is equal to mu I for I between 1 and n. We define the random variable y as the linear combinations of xi's given by the following sum. Then we have the following properties. The expected value of y is going to be the linear combinations of the corresponding expected values of the xi's. The variance of y is going to be the following mixed sum, ai times aj times the covariance of xi times xj. And finally, if all the xi's are independent, the variance of y will be the sum of the product of ai squared times the variance of xi. This is all I wanted to say about joint probability distributions for now. We are going to come back to this topic quite often when we deal with statistics. That's all for now. Thank you very much, and I will see you around.